I am not going to tell you that the climate isn't changing. So for those of you who were concerned that that was something I was going to say, or for those of you who have boycotted with that fear, no, I'm not going to say that. The geology, the science that we practice, all of us, charges us with studying the earth and what it's made out of, and all of its operative systems, and the forces that act on it, the products that result, and it then charges us with conveying that knowledge back to society at large for beneficial use. Climate's part of that. And we, as a group of scientists, have generally done a very poor job of fulfilling our ethical responsibilities in that arena. So I've portrayed this presentation as something for you to earn an ethics credit with, which all of us who have these licenses and registrations and all this stuff need to do every year. And so I am going to focus on ethical issues, but I'm also going to focus on data. Because in much of the argument and discussion that takes place in the public arena, data aren't being talked about, only models. So I want to talk about data, and I'll show you how the data compare to the models. All right? So, having said that, this will run, I'm breaking all the rules of public speaking. I'm going to try and do this in about 30 to 35 minutes, but I have 66 slides. All right? So work with me here. All right? Here's where we're headed. What are we being told? What are we hearing today? But what are the data? What are the data? You don't see much of the data. What are the takeaways that I would have you leave here with this evening? And what are your responsibilities? I've already told you you're failing to meet some of them, but what should you be doing? And will you have the ammunition to discharge those responsibilities? Right? We've been beaten with a stick for, see, I can make puns too, for a couple of decades now, and we've been told the Earth is warming inexorably, and it's going to continue to warm. That's what the modelers project. Right? And the reason they say that's happening is because of all the CO2 that we're putting in the atmosphere through the burning of fossil fuels. Thus the war on carbon. Right? We're told that the Arctic is melting, and we have shown comparator shots like this. We're told that glaciers are retreating, and yeah, okay, they are. We're told that sea levels will rise, that coastal cities will be inundated, that tropical storm numbers and intensity will increase. You've heard all of these things, haven't you? You've heard them in the last week. That tornadoes will become more frequent and intense, and that precipitation will increase in frequency and severity. This is the Danube in Austria last year. And that famines will kill millions of people. All in all, a pretty dark picture. This was supposed to... You are going to be a tough audience, I can see. Right? But what did the data show? What did the data show? All right, so let's cut to the chase. What do the data show? The data show you that the real world really hasn't warmed up very much at all in the last 40 years. Look at the scale. A couple of tenths of a degree. And what are you being told? What's the press represent to you? Well, you're being told that this is what's going to happen. And that's not what's happening. That's not what's happening. And now we can portray this a couple of different ways, so I'll give you all the versions. You ready? And these slides, these three, come from John Christie. John Christie is a climate scientist at the University of Alabama at Huntsville. He has shown all of this to Congress year after year after year in testimony. He keeps beating the drum. Right? We can do straight line projections, and here you can see all of the colored stuff. And those are the models, and that solid black line, that heavy black line, is the average of 73 models that the IPCC uses. And on the bottom, in dots and in a straight line, are what the balloons and satellite data sets show us is really happening. And they don't show a whole lot of warming. Is there some? Yes, there is. Is the climate evolving? Yes, it is. No, I'm not a denier. And then we have what the models look like if you just do it with 5-year rolling averages. And here's the average, very dark black right here. And then here's the real world. And if you reduce it, 97% of the models are well above what the data are. They don't fit. They're unable to forecast what we're seeing. Let's take a little bit longer view. Let's look back a couple of hundred years. So this is years before present on the bottom. And present in this case, at the end of the line, is 1950. All right? So we're kind of off the chart over here someplace. And there's a date marked here. This is 1820. And 1820 is used by some people as a mark for the end of the Little Ice Age. Right? Some other people use 1850. And some people use 1880. So as we go through the data, you'll see why different people use different dates to end the Little Ice Age, which ran for almost 1,000 years. Right? Here's the longer view. What I just showed you is the last 300 right here. But if you move your benchmark for what you think is normal, and you take it back to what the medieval max was, or, as many people call it, the medieval optimum, when we were growing grapevines in England, what you begin to see is that we're just now coming out of the Little Ice Age. You haven't seen that chart, have you? Now, average temperature profiles. Several agencies collect data. I'll be referring to all of them in this discussion. NASA, this is Houston, so you know who NASA is. NOAA, and Hadley, which is the British Met Office, who is linked at the hip with East Anglia. But they keep their own data set. Right? And what you'll see is that there are slightly varying data agency to agency, but generally they're pretty close. Something else you need to watch for is, well, what other agencies collect data? And how good are their data repositories? And here's an example of one where, here's in the upper chart, what you get out of New Zealand right now. In the lower chart is what their original data looked like. And as you can see, what they're presenting now isn't what they used to present. It's been adjusted quite dramatically. Now, why do you need to adjust the reading on a thermometer? What we've heard is that for a couple of decades is that the previous decade has been the hottest on record ever since temperatures were recorded. We've heard that decade after decade. All right? Well, if you measure that by daily high temperature records by year, from 1895 up through 2011 or 12, that's not the case. The hottest decade was back here in the 30s, around the Dust Bowl. Now we can declare the hottest decade another way, and we can look at it by number of 100-degree readings at all U.S. HCN stations. HCN is Historical Climate Network. That's the code. Right? And you can see again that the 1930s are the hot decade, and anything that's happened lately, the last 30 or 40 years, is within the range of normal variance. Can you guys see through me okay? Just about. Transparency has different meanings visually versus audio. Right? We're told the Arctic is melting. Okay? And a common comparator is 1984 to 2012. And here, for those of you who are map challenged, here's the north slope of Alaska, right here, right here. Here's the north tip of Greenland, here and here. All right? But why don't we see this one, which is August 212 to 213, where the sea ice is at a greater extent than it was in that 1984 picture. Don't see that, do you? And recognizing that there's variance, the kinds of things that we're seeing today reflect some variance back through time. Now, we can do the same thing for Antarctica. So this is Antarctic sea ice extent from 1979, when satellites were put geostationary above the South Pole, up through 2014. This is through January 31st of this year. And what you can see is that what's going on in Antarctica right now is actually a little bit colder than it has been for many, many, many previous years. But generally, we're working within the range of normal variance. There's nothing extraordinary happening. And indeed, if you add, as of last week, on the day that the executive office announced that it was going to take dramatic actions, and he was going to employ his pen and phone again, and you sum the North Pole ice, sea ice, and the South Pole sea ice, we're at the second highest extent since records have been taken. But you didn't hear that in the press this last week, did you? Are glaciers retreating? Well, yes, glaciers are retreating. You heard it here first. Right? And they've been retreating since 1820, when people think the Little Ice Age ended. That's where that one date comes from that I showed you in the previous chart. Long before the accelerated use of carbon-based paleocarbon fuels. I think I sputtered that one out well enough. Right? That's pretty normal. That's pretty normal. Here's what Greenland looks like today. This is ice sheet topography, so it's thickness of ice. Here's what it looked like, we think, during the last interglacial, about 1,000 years ago. 1,000 years ago. The end of the 10th century, when Vikings were settling there and naming it Greenland, and growing barley so that they could brew their ales and brews. Greenland. Right? Is sea level rising? Yes, sea level's rising, and it's been rising since about 1850. So here's the second choice for where you end the Little Ice Age, and here's why some people choose this date. It's been rising on about the same slope since 1850. 1850. And there's no change in that slope to speak of once we started burning a lot of hydrocarbons. Didn't see that last week either, did you? Have tropical storms become more frequent and intense? Now, there are two lines on this chart. The upper line is all tropical storms from 1970 through to the beginning of this year. And the bottom line is hurricanes as a subset. So you had to reach hurricane strength. And I would challenge you to find a whole lot of significant change across those two lines in the last 44 years. So no, we don't have more frequent or intense tropical storms. Have tornadoes become more frequent and intense? This data is from NOAA, and this is the annual count of strong to violent tornadoes, so F3, 1954 through 2012. Here we are out here in 2012. Right? I don't have 2013, and obviously this is 2014. We haven't finished counting it. Right? Not a big change. Everything is within statistical variance. And if you were going to point to anything, you'd point to this period back here, 1973 and 1974, which is kind of an interesting time, because 1973 and 1974, when they noted this devastating outbreak of tornadoes and 148 twisters killing 300 people and $500 million worth of damage, they said it was because the climate was cooling and we were about to move into an ice age. And I've expressed this kind of information on some university campuses, and what I'm told is, oh, no, the climate community never believed that. Really? Well, you know, the National Academy of Sciences did, and the National Oceanic and Atmospheric Administration did, and people at Columbia University did, and this is what was published in Newsweek in 1975. 1975, hold that date. Hold that date. Right? Has precipitation changed in intensity or severity? You were told this last week that it had. But no, it really hasn't. So this is percentage of area that's dry from 1900 to 2010 plus, and percentage of area in the country that's wet. And there's really not much variance. Everything we're seeing today out here at the end is within the range of statistical variance that we've seen for 100 years. Nothing extraordinary. This surprises you, doesn't it? Right? We can look at the same kind of information by looking at snow extent. So here's percentage of area, November to April, covered, percent right here, covered with snow. And indeed, if anything, we're fairly high here in 2012. This is a nice segue into California. We've heard a lot about the drought and the misery in California. And here's snowfall in gray and snowpack in blue for Donner Summit. We all know about Donner Summit, right? In the High Sierras from 1879 to 2013. And I'll draw your attention to 1881 here in yellow, 1885, 1924, and 1977. Though they're much worse than where we are today. And 77 was a real rougher because it was 2 back-to-back years. What California is experiencing today is within the range of normal expectations. So where does that take us? You guys are going to like these slides all the time. So does atmospheric CO2 really drive climate change? Well, let's look at that. Here's a pie chart for sources of greenhouse gases as calculated. Contributors define the way climate scientists like to define it. And what you and I are contributing, me more like this minute than you because I'm talking, is 0.28% of the greenhouse effect. Mother Nature, with biologic activity and volcanoes and plants and other bovine flatulence out here, provides 4.75%. And the big red piece, 95%, is all water vapor. Water vapor. Climate scientists have known forever that water vapor is an enormous greenhouse contributor. Why do you think we love the summers in Houston so much? You know? Oh, God, can you feel the CO2 out there today? It's just oppressive. We know, as scientists, geological scientists, that we've had a whole lot more CO2 in the atmosphere at times in the geologic past. We know that. We know that. The IPCC knows that. And this is out of their January report where they show all of their proxies, all the proxies for CO2 in the atmosphere. And within the last couple of million years, the range gets us all the way up above 400 and almost to 500 parts per million. We've had a lot of CO2 in the atmosphere, and a whole lot more than that in the past. Whereupon the planet undertook carbon sequestration and grew these things called the Mauna Loa seasonally adjusted CO2 level in the atmosphere. That's the standard. out there on top of that mountain. And from 2002 to 2009, we show that it increases steadily. In this magenta color is the Hadley British Met Office data, which you can see is very noisy. And you fit a line to it, you get this slope right here. All right? And this other one that's even noisier is University of Alabama at Huntsville, John Christie's data. And you fit a line to it, and you get that line. So we know that for the first decade of the 21st century, as CO2 increased, temperatures appeared to decline. Christopher Monckton in the UK has taken on this data. And he's looked at 98 through 2013, and he's fit a line to it. Okay, so in the background, you see this pale green here. That's a straight line fit to the CO2 concentration curve. That's the little wiggles right here. It's barely visible. And he said, well, here's the real data, not the CO2 data. Here's the temperature data. And he calculates, with no correlation coefficient whatsoever, a flat line. He's shortened it up a little bit, and he's gone from 2002 to 2013. Same thing. Here's the CO2 in the background. Here's the straight line fit on the CO2. And here's the best fit straight line for that data with a very poor correlation coefficient again. And then he shortened it up one more time, and he went from 2006 to 2013, and he's still got an abysmal correlation coefficient, but he's got a negative slope. And it's nowhere near what the IPCC models projected. Nowhere near it. So, the stick that we've been beaten with is wrong. Is wrong. And we're going to touch on the CO2 and the temperature correlation again as we go forward. So, you're waiting to see, aren't you? So what then is driving climate change? Well, you know, we have this little star that we revolve around on an annual basis. You know that only 1 in 4 Americans knows how long it takes the Earth to revolve around the sun? 1 in 4.
And on the street.
1 in 4. I would hope that this audience is better than that. But there's a moral here in terms of why the public doesn't get it. Right? The other thing that's in this picture is misbehavior in the sun, sunspots. Right? So what do sunspots have to do with what's going on here? Right? If we have a sun that's got a lot of sunspot activity, upper left picture, it generates a very strong solar wind. And that solar wind prevents cosmic rays and cosmic particles from entering in the upper atmosphere. We wind up with very clear skies, and we wind up with a very warm Earth. Okay? If, however, the sun is quiet, few sunspots, the solar wind is weaker, and cosmic rays and cosmic particles can enter the atmosphere, we can nucleate clouds, and we can get a cooler Earth for a couple of reasons, the clouds being part of it. Okay? We can see that in data. So the bottom line is sunspot activity from 1958 through 2010. Right? Numbers of sunspots through time. The upper curve is cosmic ray count. Cosmic ray count, making it through the atmosphere. And for every place that you see a lot of sunspots, you see a much diminished cosmic ray count. Less nucleation of clouds. Okay? Part of what's going on is that irradiance levels are up when we've got sunspots. Irradiance is what I'm going to do to that phone. Irradiance is the amount of energy that's reaching the outer layers of the atmosphere from the sun. The amount of energy reaching the outer layers of the atmosphere from the sun. So when we have lots of sunspots, here we have lots of energy reaching the outer atmosphere. All right? Makes sense? Here's how the temperature correlates. So this is several solar cycles. Sunspots on the bottom. Had forth. Hadley, Climate Research Unit, so this is East Anglia. T4 is the database. Global temperature. Here we are back in the 60s up to right here. Here's 1975 and my newspaper. And look at where the temperatures are. They're down here. And then we increase solar activity just a bit, and temperature starts going up and going up. And then we get to here, and the sunspot activity from late 1998 up through the beginning of 2009 starts to drop, and temperatures stop increasing. Temperatures stop increasing back here, all right, according to this chart. Now, what you can also plot against those two curves, here's the same two curves, sunspot numbers, sea surface temperatures here, is you can plot atmospheric specific humidity in the middle troposphere. Okay, so we're at 9 kilometers. Here's 1975, right here. This is when everybody thought that the Earth was cooling and we were going to have an ice age. And then things started warming. Sunspot activity increased. We warmed some more. And then you get out here, and things started falling off in cycle 23. And the humidity starts going down. And here's where we are today. Well, last month, 2 months ago, March 2014, cycle 24, we're on the down select cycle. We're diminishing sunspot activity. We're diminishing the amount of irradiative energy reaching the atmosphere. And where do you think that line is going to go? And where do you think this line is going to go? And I can tell you that the people who study the sun say that for the next couple of decades we should see things cooling. Right? Let's look into the past. And I don't know how they did it. You know, they probably hired a bunch of geophysicists with pointed black hats and moons and stars on them, put them in a dark room, but they reconstructed solar irradiance all the way back to 1600. From right here in 1620 or 30, out through here is where we've got the little ice age. Okay? If we zoom in on just this piece right here, the right-hand end of that chart, and we plot temperatures versus solar irradiance, we get a pretty good fit. The sun and the humidity in our atmosphere are what drive climate change, as best explained by all these data. All right. Solar activity cycles 1749 to 2040. So here's a projection. Here's 24. This is the one we're coming off of. Here's the projection by the solar modelers, the people who look at the sun, for what they think we're going to see for solar radiant energy and sunspots in the next cycle. And these are only 11-year cycles. This is an 11-year cycle. We're going to see this pretty soon. And they suggest that we're moving into another one of these areas. The Dalton minimum doesn't refer to temperature, it refers to sunspot activity. And that we could get very cool in the coming decades. And you didn't hear that last week either, did you? All right, so global warming. Just the facts. The historical rate of sea level increase is 0.07 inches per year, which is not particularly catastrophic and may even go down. All right, that translates, for those of us who are geologists, you slide the decimal place 2 and you get inches per 100 years, right? So 7 inches per 100 years. There are no more droughts or storms than normal. I've just shown you that data. Ice melting is normal for an interglacial period, which is what we are in. CO2 is not the cause of global warming. It doesn't correlate with temperature. Temperature increases may cause CO2 increases, to the extent that there's any loose correlation. Solar activity has a much stronger impact. And water vapor in the atmosphere demonstrates a much more compelling correlation with temperature, as I just showed you. And we know that water vapor is an even stronger greenhouse contributor than CO2. From the mid-1800s to 1998, temperatures increased by 0.8 degrees centigrade. 0.8 degrees in almost 200 years. From 98 to 2007, temperatures were fairly flat. Right? You'll hear this 1998 figure. People will say, well, it's 1995, it's 1997. Someplace in the mid to late 90s, we stopped warming. And from 2007 to 2012, temperatures fell by 0.2 or 0.3 degrees centigrade. Now, my buddy Albert said once that, no amount of experimentation can ever prove me right, but a single experiment can prove me wrong. Right? Ladies and gentlemen, we've been running the whole Earth experiment for 120 years. For 120
years. Because one experiment did prove them right.
For 120 years, what we've seen is observations in temperature, in red, and a line fitted to it in the dark dashes here. And green is CO2. So from 1895 up through approximately 1915 to 1920, as CO2 increased, temperatures fell. From the World War I period up through the early 1930s, temperatures rose as CO2 went up. Things flattened out a bit during World War II, but generally from the late 1930s through the early to mid-1970s, temperatures fell as CO2 ramped up even more dramatically with the post-World War II industrialization here in the United States and in the Far East and in Europe, as the Marshall Plan kicked in and people got back to work instead of war. And then from 1975, remember my 1975, we're going to go into an ice age, up until nearly 2000, temperatures went up with CO2. And then as I've shown you, a couple of people are looking at this very small piece of data out here on the end, and they're saying, we're already falling. We're already falling. So is climate changing? Yeah, climate's changing. Has it gone through these cycles before? Yeah, it has. And CO2 is not the driver. Now, once upon a time, when all of us were in school, we liked to finish our presentations with fancy sunsets. And I thought about doing that with this. You ready? Quotes from the National Climate Assessment Report that came out last week.
Oh.
All right? You ready for this? I bet you didn't hear any of these. There has been no universal trend in the overall extent of drought across the continental United States since 1900. Other trends in severe storms, including the intensity and frequency of tornadoes, hail, and damaging thunderstorms, are uncertain. There is a lack of any clear trend in landfall frequency along the eastern U.S. and Gulf coasts for hurricanes. And when averaging over the entire contiguous U.S., there is no overall trend in flood magnitudes. Didn't hear any of those things, did you? Not even close. So with that, I will thank you for your attention. You've been a very nice audience, and I'll take you back to the amount of money going there. I can give you a little anecdote. One of the last things I did at BP was CO2 sequestration work. And there was a fellow in our London office who had done his graduate work in Australia. And he told me about having been back in Australia on a field trip and meeting up with a professor that he'd had previously who had thought that the CO2 climate change stuff was a bunch of nonsense when he was a graduate student. And now this professor was espousing exactly the opposite. And my colleague asked, well, how can you be doing this? He said, well, that's where the money is. That's where the money is.
Yes, first, I have two questions. First, I want to thank you. I know it takes a lot of effort to put a talk like this together.
Thank you.
My first question is, you know the 9 oil companies, intermediate to major size, are planning on some kind of carbon tax in a long-range financial plan. One of those is ExxonMobil. My second question is, are you planning on submitting this to a peer-reviewed journal? The reason why I say that is because I've given 4 talks at HGS. Each one of those were based on studies that I did for peer-reviewed journals and based on data that I collected and did most of the analysis on.
This isn't my data. These data were provided to me by other scientists who have submitted their work, and a lot of this has come out of peer-reviewed places, and if it wasn't peer-reviewed, it came out of sworn testimony to Congress. So John Christie sent me his stuff from Alabama, and that was congressional stuff that was submitted under oath, which, well, I won't go into that. I am aware that several companies are planning to absorb a carbon tax. I don't think they have a choice but to make that kind of plan defensively, because that seems to be where this administration is going. I think it's an inappropriate tax, and I think it will devastate our economy, and that China and the rest of the Far East that's ramping up its industrialization will laugh all the way to the bank.
Well, I think ExxonMobil is hoping on carbon tax because they'll be able to sell more of their gas versus people buying coal.
I don't follow exactly what ExxonMobil's corporate policies are.
Go to the website.
There are 8 billion websites. One in the back there.
Yeah, so why do you think the mad hockey curve is wrong? You said it was wrong. Do you think it's intentionally manipulating the data, or what makes it wrong?
My impression is that it was a manipulation of the data to make a political point. And if you look at the way they've exhibited that data, it doesn't reflect the changes in temperature for the period of time they cover that I was showing you the raw data show.
On a couple of the slides, you went back to the medieval warming period, but on the vast majority of them you weren't. I'm assuming that's simply because there's no way to extrapolate backwards any kind of data.
To the best of my knowledge, there's not a way to extrapolate some of those data back. Everything that I showed you, as I just said to this other gentleman, is stuff that other scientists have done, and they've taken it as far as they can take it. And I'm just compiling what's available in the literature. You know, many times I get quizzed about, well, why aren't people speaking out more about what their concerns are with current policy and current direction? And my point is that people are speaking out, but they don't buy their ink by the barrel.
It's really a follow-up question to that. Are you aware of anyone taking some of the more recent data we have and attempting to model backwards to the MWP, to the medieval warming period, to see if the correlation, and I'm mainly thinking of solar scientists, astronomers, as opposed to...
Well, the solar scientists, I took you back to 1600.
Right, but then trying to take that data, the data we do have, and try to push back through within the MWP context. Are you even aware that anybody's been doing that?
Okay, can you hear the questions?
Not right.
The question is whether or not some of the scientists studying solar data have tried to model backwards past where the left end of my charts was. And no, I'm not aware of any modeling that's gone back that far. No, that one curve of solar irradiance that I showed goes back to 1,000, because we got back pre-modern minimum, and we got back to the end of the medieval warm period, and that's when people started counting sunspots. Before that, there's no data.
I like to take the task of people who say ever since we've been having measurements of temperature, they've been going up. Well, Mr. Fahrenheit invented his thermometer and his scale in the middle 1700s.
Yep. Jeff?
Yeah, Rusty, could you summarize the mechanism of the solar irradiance again, and how that affects, what was the mechanism for that?
When we have a lot of sunspots, we have the sun putting out a lot more energy, right? And it has a solar wind that's got a particle component to it, right? As well as a wave component to it. And what that does is that extra energy deflects some of the cosmic radiation coming in from other directions, and the particles coming in from other directions, cosmic particles. When we have, and we get at the same time with the extra irradiant energy hitting the outer layers of the atmosphere. That's what total solar irradiance is. You diminish the sunspots, you diminish the solar wind, you diminish the energy that's being put out, things get a little cooler, but as well, now the cosmic rays and the cosmic particles can make it into the atmosphere and can perform nucleation or allow nucleation so that we get more clouds. Does that help?
Yeah.
One more question, we'll call it.
I'm curious what are some of the drivers for atmospheric humidity at 9 o'clock?
The drivers for atmospheric humidity? Well, 2/3 of the Earth's surface is covered with water. And it's going to have a partial pressure into the atmosphere as it warms and as things evaporate and as we come to evaporative equilibrium. That's what puts that there. So,
All right, well, thank you
Thank
very
you.
much. Let's give our speakers a lock. And since